All right, everyone. Welcome to your last video of the school year. You know, this is not technically due until Friday the 22nd. You can, of course, turn it in a few days after that if necessary, but I wanted to get this video out early to you guys so that you could finish up if you want to. And also, I know some of you guys have AP exams, and I wanted you guys to be able to work around those. Now, first off, um, I wanted you to look at these numbers here, 20%, 1 over 5, and 2/10 or zero point 0.2, and see if you could figure out something about these numbers, all right? And what you should be able to figure out is all these numbers are exactly the same number. They're just expressed in different ways. And that leads into what we're going to be doing in the first part of this lesson, anyways, is expressing numbers in different ways. Sometimes we express them in radians, like these numbers here on the unit circle. Sometimes we express them in degrees, like these numbers here. All right. And sometimes we can express them as radians in decimal form, which is not what these are. These are what we call radians expressed in terms of pi, but we can also express radians in decimal form. Okay. And what one other reason why I have this unit circle up here is primarily we've been working on these points here. You know, there's 3 points here and 3 points here, and 3 points over here and 3 points over here. And all of these points are formed by either 30, 60, 90 triangles or 45, 45, 90 triangles in the unit circle. A lot of what we're going to be dealing with today is the points in between, all right? So we're not going to have, exact, we're going to be doing a lot of rounding. Let me put it that way, okay? So the first part we're talking about today is section 13, topic 5, more conversions with radians. And they're asking us if there's another way that we can write 2/3 pi radians. And there's actually a couple different ways we can write it. And I wanted to show you guys both of those ways. The first way that we could write it is we could write this as a degree. All right. So if you guys remember what you're supposed to do in order to turn uh, 2/3 pi radians into degrees, and another way to write 2/3 pi radians as radians would be 2 pi over 3 radians, is we are supposed to take this pi out and replace it with 180 degrees. So this would be 2 times 180 degrees over 3. And of course, 2 times 180 is 360, and 360 divided by 3, I hope you guys know, is 120 degrees. So there's one other way that we can rewrite this. Now, what we're going to learn in a second is how to write this radians in decimals, okay? And I'll bring you that one right back, all right? So how can we write radians in decimal form? Guys, I want you to look at what we were just looking at, 2 pi over 3. And it's very simple to figure out how to write this in decimal form. Do you see a number on the screen or a symbol that's on the screen that we can rewrite as a decimal? And the answer, of course, is yes. This symbol right here can be rewritten as 3.14. Now, I know 2/3 can be rewritten as 0.67, and that's fine too. You know, if you want to write that as 0.67 and then rewrite this as 3.14, then you could write the radians in decimal form of this as well. All right. But this is really the only one that we need to change. So what we end up with is 2 times 3.14 divided by 3. Okay. So let's go ahead and do that. 2 times 3.14. Move this over here. 2 times 3.14. We get 6.28. And we're going to divide that by 3. And we get 2.093333. Let's just call this 2.09. Okay. So this is approximately 2.09 radians. Okay, that's another way to write 2 pi over 3 radians. Okay, so this is radians in terms of pi, and this is radians written as a decimal in decimal form. Okay, so this is about the same thing, and I use the squiggly equal sign because this is not exact. You remember there was 0.3333 repeating, and that's only with us using the short version of pi. If we use a longer version of pi on the calculator, in other words, let's see, 2 times this version of pi, and then divide by 3, we get another slightly, 2.09439 longer decimal version. So again, this is just an approximation, while this one is much more accurate. Remember, this symbol stands for a number that you could probably never write if you spent your whole life writing it. Okay. So the question here is, if we're given radians in decimal form, how do we go back? How do we go back to what we just saw a second ago? All right. And so let me give you an example. Let's say we had 2.5 radians. Okay. And we want to write this in, terms of pi. So if we change this here to 2.5 times, and notice that we can't multiply this times a number that's actually going to change this number, because that would change its value. So the only thing that you can multiply something by, the only number you can multiply something by and not change its value, is to multiply it by 1. All right. Well, we know that we want the pi symbol to be in our, you know, radians in terms of pi form. So we know that the pi symbol we're going to have right here. And then what is the number that we're going to put on the bottom that is going to represent pi? And that would be 3.14. All right. So when we multiply this across, we end up with 2.5 pi over 3.14. And the only thing that we would do at that point, guys, is just to straighten this out a little bit. What I like to do is make these numbers whole numbers, and we can do that. If you see this decimal needs only to move one place, but this one needs to be moved 2. So we're going to go ahead and move both of them 2. So what this ends up being is 250 pi over 314. And then both of these are still even, so we can reduce this fraction down a little bit. If we cut both of those in half, we end up with 125 pi. And then 314 cut in half is 157. And I don't know if there's any number that goes into 125 and 157, but I doubt it. So you're going to use this 157 quite a bit. But 125 pi over 157 radians is the, in terms of pi version of 2.5 radians. All right. Now, how about if we're given radians in decimal form, can we convert it to degrees? All right. Well, we could, if we went back to this problem right here. Remember, to convert this into degrees, we just got to change this to 180 degrees. And it'd be 125 times 180 divided by 157. We could do that if we wanted to do that. That wouldn't be that big of a deal. But there's a little bit faster way to do it if you wanted to do that. So what we end up doing is we're going to multiply times, well, basically what we're going to do is we're just going to step all the way back here and just change this to 180. All right, so we're doing the same thing, we're just doing it much faster. All right, so for instance, if I had something like, let's say, 3.7 radians, all right, to convert this into degrees, I'm just going to do times 180 degrees over 3.14. And then I would just throw that in the calculator. And so in the calculator, I got 3.7 times 180. And then I'm going to divide that by 3.14. And I end up getting, that's about 212 degrees, somewhere around that. Again, it's not 100% accurate. So this should really kind of be a squiggly equals, right? But that's approximately what it is. All right. Everybody good with that? And by the way, this kind of makes sense. Remember, if you're talking about pi radians, that was halfway around the circle, pi radians. Remember? Then that would be 180 degrees. Well, 3.7 is a little bit more than this, remember, because this is 3.14. So isn't 212 a little bit more than 180 degrees? I mean, it just kind of makes sense. All right, so we're going to try to convert 1/4 radians into degrees. All right, 1/4 radians. Again, I want you to think about that. 1/4 radians is not very far around the circle. Remember how far is it all the way around the circle? It's 2 pi radians. So 2 pi radians is about 6.28 radians. Okay. So we're only going 1/4 of a radian. So this in degrees should not be very much at all. All right. So the way that this works again to convert this to degrees, we're going to take 1/4. All right. And then we're going to multiply it times, since we want this to be um, degrees, we know we're going to multiply this times 180 degrees over 3.14. All right. Now, again, we could have written that as pi over 3.14 because that is, again, still 1. And this is technically also still 1. It's just converting um, radians into degrees. So if you want to, take it step by step, you're talking 1/4 times pi over 3.14, and you could go ahead and get that, which would be pi over 12.56, I believe is what this is, and then you change this into 180 degrees over 12.56. But it's just a little bit faster to just go straight into this. All right, so 1 times 180 is 180, and then 4 times 3.14 is 12.56, and then we just do this on our calculator, and we get 180 divided by 12.56. And as you notice, this is a whole number being divided by a couple decimal places. So we're going to end up with a decimal place. That's okay. And we get about 14.33 degrees or so. So this is around 14.3 degrees. Okay. Again, we used a short version of pi. If we use a longer version of pi, we would get a longer decimal, but it would still round about to the same thing. All right. So it asks us here, what is the radian equivalent in decimal form of 1 degree? Guys, I want you to think about that. How big is 1 degree? All right, 1 degree is very, very small. It's really not going to, take up that much space. Okay, and this is a conversion that we haven't done yet, so it is kind of interesting looking the way that it looks. So again, we have to take this degree version, all right, and we have to multiply it times. And what we want to do is we want to multiply it times another value of 1. Okay, now that value of 1 could be pi over pi or pi over 3.14. But in order to get rid of the degree symbol, this is currently in the numerator. If you think about this, this is over 1. So in order to get this degree symbol, get rid of it, we're going to take our 180 degrees and we're going to put it here. What that's going to do is cancel out those degrees. All right. And then our pi, we're just going to leave it up here. Okay. Now, it does say in decimal form, so we're just going to write 3.14. If it said in terms of pi, we would just leave pi up there. All right. So now we got basically 1 times 3.14, which we know is 3.14, and 1 times 180, which we know is 180. And then we're going to go ahead and divide that. So this is going to be 3.14 divided by 180. And we get 0.01, let's say 74, right? 0.0174 radians. And we said just a few seconds ago that that was going to be a very small amount of radians. Remember, it's only 6.2 radians all the way around the circle, while at the same time it's 360 degrees all the way around a circle. So if you're only dealing with 1 degree, which is a very small part of this, 1/360th, then we're dealing with 1/360th of these as well. So this is a very small part of our 6.28 radians. Okay. All right, couple more just so you can practice here. All right. Convert 32 degrees to radians in decimal form. Again, if we wanted to convert this into radians in terms of pi, you remember last time we said we are going to take 32 degrees and we're going to multiply it times um, pi over 180 degrees. All right. But this time to get the decimal form, we're just going to change this to 3.14. Okay. So really, you're just going to throw this into your calculator. 32 times 3.14. We're going to divide that by 180 degrees. and we get 0.558 or 0.5, let's say 0.56. 0.56 radians. Again, this is rounded, so we're approximating 0.56 radians. Okay. I mean, it depends on where you need to round. It should tell you where to round, or if you have a multiple choice question, you should be able to see where to round. All right, it's not that big of a deal. All right, let's see. What is the degree equivalent of 1 radian? The degree equivalent of 1 radian. So if you think about that, if you remember with a circle, let me just draw a circle here really quick. If you think about that with a circle, all right, we're trying to figure out how many degrees 1 radian is. Now, 1 radian, if we're starting at the center of the circle, let's say right here. Remember, 1 radian, if this is 1, all right, if that's the radius, 1 radian would be pretty much the exact same. However far it is from here over to here, that's exactly how far around the circle we want to go here, right? This thing here should be the exact same length as this thing here, okay? So that's how, the length of 1 radian would be, all right? So the way we're going to do that is we want it to be degrees, so we know we're going to have 180 degrees somewhere in here. So we got 1 radian times, and remember we're going to put 3.14 pi down here, okay? And then we're going to put 180 degrees here to get, and remember, this right here is still just 1. Remember, this is pi over 3.14, but we said to convert degrees into radians, radians into degrees, we can substitute freely 180 degrees and pi, all right? So 1 times 180 is 180 degrees, 180 degrees divided by 3.14, well, let's see, 180 divided by 3.14. And so you can see that each radian is around, let's say, 57.3 degrees, okay? So this angle right here is what we're talking about, all right? This angle is about 57.3 degrees, okay? Any questions on those conversions? All right, so here I just got a table that has a few. We're not going to do all of these, but I just wanted you to see how to bounce around between all of these different types of um, conversions. We've got some radian measures in terms of pi over here in these columns. We've got some radian measures in decimals in the center. And we got some radian or some angle measures in degrees over here. And I just wanted to do at least one of each of these to where we're starting in a single spot and we work over to the other two. So I'm only really going to concentrate, let's say, on we'll do these over here. I'm not so worried about these, although I do want to talk about this one. So we'll probably do all of these and then we'll do this one here. All right. So some of these are very simple. All right. For instance, we did learn in last week's lesson or this week's lesson, how to convert from radians to degrees is very simple. All we're going to do is we're going to take this right here, and we're going to change that to 180 degrees. All right, so this is going to be 3 times 180 divided by 4. All right, so 3 times 180 gives us 540 divided by 4 gives us 135 degrees. Okay, 135 degrees. And to convert radians in terms of pi into decimals is super easy. Instead of changing that into 180, we're just going to change this into the decimal version of pi. All right, so that now is going to be 3.14. So 3 times 3.14 divided by 4. So 3 times 3.14 divided by 4. And we end up getting about 2.355. We could round this anywhere you want, or we could just leave it like it is. We could, well, let's do nearest tenth. So that's about 2.4. So this is about 2.4 radians. Okay, so that's how you convert in terms of pi radians into both the decimal radians and degrees. It's very simple. The only thing that gets changed is this pi symbol. All right. So last time we learned how to convert degrees into radians in terms of pi. All right, if you remember right, what we're going to do is we're going to take this 55 degrees, we're going to times it by, right, and we need to get pi into this, right? Remember that we need to get pi into this, and the denominator we're going to get is 180. All right, And so what this is going to do is it's going to put pi in, and at the same time, it's going to get rid of the degree symbol by canceling these out. So we cancel those out, and so we're going to end up with like 55 pi over 180. Now, we do need to try to simplify this, and I'm trying to think what numbers go into 55 and 180, and the one that jumps out immediately is going to be 5. So 5 goes into 55 11 times. So this turns into 11 pi over, and 5 goes into 180. Well, 10 goes into 180 18 times, so 5 goes into 180 twice as many times because it's twice as small. So that's going to be 36 times, all right? And the 11's a prime number, so we can't do anything with this, so it's going to be 11 pi over 36, okay? Now, to convert this into this one, all right, it's very simple. All we're going to do is change this into 3.14, okay? So this would be 11 times 3.14, and divide that by 36. Oops, 36. And we end up getting about 0.959, so about 0.96. This is about 0.96 radians. All right. Now, the most difficult one for sure is when you're starting with radian measures as a decimal. That is the most difficult one. The problem is it's really kind of hard to remember, I think, for a lot of students. You know, how do I convert this here into, you know, degrees or radians? What do I do? You know, which one do I do? Just remember what symbols you want to be in your new answer, and that should help you out a little bit. For instance, if we want to convert this into radians, we want the pi symbol to be over here somewhere, all right? So that means we're definitely going to have to multiply this times something that has pi on the top, all right? Now, for us to do this one, we're just going to end up putting 3.14 on the bottom because we are not using degrees at all, so we are not going to use 180, all right? So this is what you end up doing, all right? Now we end up with 3.2 pi over 3.14. And then we want to try to make these whole numbers. So that is the same thing as 320 pi over 314. And you notice that all I did was I moved these decimals to the right too. As long as you move the decimals the same amount, you're not doing anything. So now I've got whole numbers. I've just got rid of the decimals. Both of these are even. And so half of 320 is 100 and let's say that's 60. So we got 160 pi over 157 pi. Remember, I'd said this 157 was going to come up quite a bit. And I don't believe there's a number that goes into 160 and 157. So this is going to be 160 pi over 157. All right. And once we have this one, it's really simple just to go straight from here over to here. We're just going to replace this with 180. All right. Now, if you wanted to go straight from here over to here, you could do that. It wouldn't be that big of a deal. Just the original problem, all you would do is you would change this to 180 degrees. All right. So it would be 3.2 times 180 divided by 3.14. But as it is right now, we already got the work done. You know, we could use this or not. So 160 times 180 divided by 157. And we end up with, it's about 183.4 degrees. All right. All right, so the last one on this side over here, 3 pi over 2, and hopefully you recognize this number and you're like, I remember that number from when we were working on this the other day. All right, if you remember right, on a unit circle, all right, when we start and we go all the way around the circle, all right, when we start right here, pick a different color. When we start right here, when we go up here, this is, right here is 1/2 of a pi, if you remember. When we go all of radians, when we go all the way over to here, we have now gone pi radians. When we go all the way down here, we've gone 1 1/2 pi radians, or another way to put that is 3 pi over 2 radians. When we get all the way back over here, we've gone 2 pi radians. Okay, so these numbers is one of this number right here is one of those numbers. It's right here. Okay, so to convert this into radian measure as a decimal, again, all you have to do is to convert this into a decimal. So 3 times 3.14, right? 3 times 3.14 divided by 2. We get 4.71 radians. All right, and to convert this into decimals, we're just going to change this to 180. And I hope you guys know the degree measure down here, for starting from here, going all the way around to here. I hope you guys know that degree measure. So 3 times 180 divided by 2, 3 times 180 divided by 2, and you get 270 degrees. Okay, so you can do these over here if you want. The only one that I did want to do really quick one time, because I thought it was kind of interesting, is this one right here. 5 pi radians. Now, I told you already that this is 2 pi radians. All right, so that means we went all the way around the circle. That's 2 pi radians. Go all the way around the circle again. That's 4 pi radians. We go all the way back over to here. Now that's 5 pi radians. So this, you're talking about more than, it's basically 2.5 times around the circle. Okay, so again, to convert this into radians as a decimal, this just needs to be 3.14. So 5 times 3.14 gives us about 15.7 radians. Okay. And again, think about it. How far is it all the way around the circle in terms of radians? 2 pi. Well, what's 2 pi? 2 times 3.14 is 6.28. So every time we go around the circle, that is 6.28 radians. All right. So 15.7 radians, yeah, that's more than 6.8. So we're going more than one full time around the circle. We're actually going more than 2 full times around the circle. Now, let's see, how do we convert this into degrees? We're just going to take this pi here and change it into 180. So 5 times 180, in other words, 5 half times around the circle, right, is 900 degrees. So 900 degrees, 900 degrees is 2 full times around the circle plus 1 more half circle, right? 360 plus 360 plus 180. And that's how we get this 900. Okay. Now, the last thing that you need to know before you're able to do your check your understanding questions is what in the heck is coterminal angles? And that problem that we just did kind of gives you a little bit of a quick sampler of what a coterminal angle is. All right. So angles that share the same initial side and the same terminal side are what we call coterminal angles. Now, let me explain. This angle right here is 30 degrees. Do recognize there is another way to write 30 degrees. You can write 30 degrees as we multiply that times pi over 3, I'm sorry, pi over 180, all right? This would be 30 pi over 180, which ends up being 1/6 of a pi, or pi over 6. So this is the radian version of it, pi over 6. So this angle starts here and stops here. So it starts at the initial side and it goes to the terminal side. All right. A coterminal angle to this would be one that starts here, right, passes through this, continues all the way around the circle, comes back and stops here again. All right. That is a coterminal angle. Now, how many degrees is that? Well, one full time around the circle is 360 plus 30 more degrees. That would be 390 degrees. That is a coterminal angle, right? That is a coterminal angle. All right. If you were to do that again, go all the way around one more full time and stop here, that's another coterminal angle. All right. Now, again, this angle measure here has another way that you can write it. So 390 degrees times pi over 180. Sorry, these cancel out. All right. And so you get 390 pi over 180 pi, which we can knock that out. And then it looks like 3 goes into both of those. 3 goes into 390 13 times. And 3 goes into 18 6 times. So 13 pi over 6 radians is another coterminal angle with this 30-degree angle. that we had before, this pi over 6 angle that we had before. Also, if we started here, right here, let me use a different color. If we started here and we went back around this way, okay, that is another coterminal angle. Do they share the same initial side? Yes. Do they share the same terminal side? Yes, they do. It's not about their degrees being the same. It's about where they start and where they stop. Okay. And even if we went all the way around and then we stopped here again, or sorry, we stopped here. Um, get rid of that part. That would be another coterminal angle. So remember when we go rotate this way, these are negatives. All right. So let me just give you one more based on that initial one that we had. All right. So let's talk about this one right here. If we started here and we went to right there and we stopped, that coterminal angle, if you think about it in degrees, it's 360 all the way around, but we did not go this 30. We are now talking about a 330-degree angle. That 330-degree angle is coterminal to the original 30-degree angle because it has the same initial side, same terminal side. And another way to write this again would be 330 pi over 180. But of course, sorry, this would be a negative because we went, you know, clockwise. Clockwise rotations are negatives. So this is a negative. We've got to cancel that out. And again, I think 3 goes into both of those. Yep. So we got 11 pi over 6. So negative 11 pi over 6 radians is another coterminal angle. All right. So you do have one question in your um, check your understanding questions that talks about coterminal angles. Okay, so anytime it starts at the same initial side and ends at the same terminal side, regardless of the direction that it goes, how many times around the circle it goes, those are what we call coterminal angles. All right, so you should be able to do the check your understanding questions for section 13, topic 5, which is called more radian conversions on algebration. And once you're done with that, you can jump into the very last section that we're going to be working on this year. All right. And I'll see you guys there in just a minute, hopefully. All right. So the last section and topic we're going to be working on is about, they call it arc measure. I really don't like the way they say that. To me, it's arc length, but I'll go with arc measure. So first thing they say is, what is the name of the part of the circle between points S and T? And you guys should have learned these in geometry. This is called an arc, A-R-C. All right, arc. This one is technically called a minor arc because it's less than half the circle, but we don't really care that too much about that here in this class. We're just going to call it an arc. Right? And if you remember back in geometry, you called it arc ST. Okay? So we're talking about the distance from here to here along the curved surface of the circle. All right? Now, we're not going to go through this a whole lot. I'm just using this diagram here as a to show you a few things. First off, this central angle right here, we call this a central angle because it comes from the center of the circle. This central angle right here, this measure. This, again, is what we call angle theta. So when you see this symbol right here, theta, all right, we're talking about this angle measure right here. Now, most of the time, we're going to be talking about it in radians, not in degrees, but sometimes it's going to be degrees. Another thing that we need to talk about is the radius of the circle, how far it is from here all the way over to here. And a third thing we're going to talk about is the length of this arc. So these things are all related to each other. All right, we're going to figure out a formula here in a minute that relates angle theta to the length of the radius to the length of this arc. All right, that's what it's all going to be about. Now, do recognize, guys, here's the big thing. If we were to take this circle, all right, and we were to expand this circle out, let me see if I can do this as accurately as possible. We're going to expand the circle out a little bit, let's say. Well, let's shrink it down. Let's shrink it down because that way I can. Okay, so if we shrink it down, watch what changes and what doesn't change. Would the angle measure from this original angle theta from here to here, would that change at all? Depending on if it's going out to the larger circle or if it's coming only out to the shorter circle. all right, the smaller circle. And hopefully you realize this angle measure does not change. It's still the same angle measure. Would the radius change length? We used to go from here all the way out to here, and now we only go from here to right there. And you can clearly see that the radius has shrunk, all right? And what about the length of the arc? It used to go from here all the way over to there, all right? And now it goes from here all the way over to here. And I hope you guys can see that that is definitely shorter. Okay, that shrunk as well. So there's a, there's a definite relationship between these three things. Now, if we did make angle theta bigger, right, recognize that the radius wouldn't change necessarily, but this arc length would also change, right? The length of this arc would change. So they're all interrelated to each other. And we're going to come up with that formula here in just a second. So this is the way that we're going to come up with that formula. I have a little picture over here that's going to help us, straighten this thing out. So first thing here, we've got the first column contains the radius size of the circle. The second is the circumference of the circle. This is a formula you guys should absolutely be familiar with. This gives us particular central angles to look at in both degrees and radian form. And then we're going to find out the ratio of the central angle to the full circle, to 360 degrees. And we're going to find the length of the subtended arc. This is what this is called. This red curved arc is the arc that is subtended, okay? And we call that S. All right. So in other words, how much of the arc gets cut off by the central angle measure. All right. And at the end, we're going to put S and we're going to put it over R. Again, R is the radius. S is the length of the subtended arc. All right. So let's take a look and see how these are related to each other. So first, the circumference of the circle. Well, it's going to be 2 times pi times the radius. And we know the radius here is going to be 1. So 2 times pi times 1 we know is just 2 pi. All right. Then we're going to take the ratio of the central angle to 360 degrees. Well, the ratio of the central angle, again, to 360 degrees, this is 60 out of 360. Okay, so this is this value over 360. And we find out that that is 1/6. Okay, so the length of the subtended arc, right? So if the whole distance all the way around the circle is 2 pi, and we're only going 1/6 of the way around the circle, we're going to take that 2 pi and we're going to multiply it times 1/6. And I hope you guys recognize, again, when you take a number and you multiply it times a fraction, you just end up multiplying by the numerator here. So we end up with 2 pi over 6. And this can be simplified. If you notice that, 2 goes into both of those. And that's just going to end up being pi over 3. All right. And then, so we're going to take this pi over 3 and put it over r. Well, pi over 3 over r, pi over 3 over r, which is 1, is just pi over 3. All right? So, how about the next circle? We don't need to really do all of these. I'm going to save a little bit of time. We'll just do the first couple. All right, so this is going to be 2 times pi times the radius, which is 2. All right, and so 2 times pi times 2 is going to be 4 pi. All right, so the ratio of the central angle to 360 degrees, again, we're talking about this being 90 degrees out of 360 degrees. And I hope you guys recognize that that is 1/4 of the circle. Think about it. Is it 90 degrees, 1/4 of the circle? Okay. And then what we end up doing is we're going to be taking the original 4 pi and multiplying it times 1/4, this value here. Okay. So if it's 4 pi, all the way around the circle, how far is it? 1/4 of the way around the circle. Well, that would be 4 pi over 4, which is just going to be pi. And we take this value here and we put it over r, we got pi over 2. Okay? And that's just what we end up with. Now, I want you to take a look at this and notice, and this would continue if we did this here. Notice the pattern. All right, guys? You see this number that's over here, the central angle measure? it's the same as the number that's over here. This number here is the same as the number that's over here. So there's a relationship there, all right? The central angle measure, which we are going to call theta, right? The central angle measure, which is we call theta, is equal to the subtended arc, the length of this subtended arc, over the radius. So in other words, we have this value here, theta. It is equal to this value, which we call S, over this value. So theta equals S over R. Okay, and recognize that it always equals the radian version. It doesn't really, I know it equals the degree version too, but it's readily apparent that it equals the radian. So we're normally going to be writing this in radian versions. Okay, all right. Now, I did write a couple other versions. This is the one that we just wrote a second ago, and I got these here just by moving these things around. And it's a really good idea to do that. It kind of helps you to not have to do reconversions every time. So let me show you how I got, for instance, this one. If I wanted to get S by itself, I could multiply both sides by R. Everybody see that? So when these cancel, I'm left with S equals theta times R. Yeah, S equals theta times R. Okay. If I was with this version here and I wanted to get R by itself, I could divide both sides by theta. And you can see that R equals S over theta. R equals S. So these are all just the same versions of this right here. It's kind of like the distance, rate, and time problems that you have distance equals rate times time. Well, that means that distance over time equals rate, and you can convert them. So let's see how we can use this. All right. It says find the length of the arc subtended by a central angle measure of 315 degrees in a circle whose radius is 20 inches. Okay. So the math that we're going to do here, all right, um, you just have to find out what are you looking for. Find the length of the arc subtended. Now we know that that is S. So that means the other two things that they're going to give us is the central angle measure, 315 degrees, and the radius, which is 20. Now remember, this really works when this theta is written as a radian. Okay, so we need to take this 315 and convert it into radians. So this 315 degrees is from here all the way around over here. Okay, so 315 degrees, to convert that into radians, we have to multiply it times pi over 180, if you remember. All right, so this gives us 315 pi over 180. And we just got to figure out what number goes into both of those, and I believe 45 does. All right, so let's see, 315 divided by 45 gives us 7. All right, and 180 divided by 45 gives us 4. So this is 7 pi over 4. So this is theta, okay? So theta equals the subtended arc length divided by r, but we're looking for the subtended arc length. So this means this is the formula we want to use, all right? So we've got subtended arc length equals theta, which we already know is 7 pi over 4 times, and we're just going to multiply it times the radius. Well, the radius is 20 inches. Okay, again, a whole number times a fraction. It's very simple. Just multiply the numerator by that. All right, so it's going to be subtended arc length equals 7 times pi times 20 over 4. All right, and I'm assuming that we're going to want to find out the length of the subtended arc. We're trying to find out how far it is from here to here in decimal version. Okay, so let's find out. Let's throw this in our calculator. So this right here we know is 3.14. Okay, so 7 times 3.14 times 20. Then we're going to divide this by 4. And we get 109.9. And oops, sorry, I mismarked this before. We're actually going this way, starting here and working all the way around the circle back to here. Okay, I know that's sloppy. Who cares? All right, so we end up with that being 109.9 inches or so. Okay, or about 110 inches. Okay, so that's how that works. Again, you're just going to have to change theta into a pi version in terms of pi version of radians, and then you just pick which formula you're using based on whatever you're looking for being the isolated variable. Okay, yeah, you can pick a different one if you want. For instance, if you were being a silly person and you said, well, I don't like that formula, I want to use this one, right? Well, you're talking 7 pi over 4 equals the s, the unknown, divided by the radius, which is 20. And you go, all right, what do I got to do to get s by itself? Oh, yeah, I got to multiply both sides by 20. And you end up with the same thing that we just did right here. Okay, so it's just a little bit faster to pick the version that's already set up. So without a picture this time, find the measure of the central angle of a circle with radius 3 centimeters that subtends its arc whose length is 2 pi centimeters. Again, the question is, what are we looking for? Okay, find the measure of the central angle. Guys, the central angle is theta. Okay, so find the measure of a central angle of a circle with radius 3 centimeters that subtends its arc whose length is 2 pi centimeters. Now, they don't say if they want that in degrees or radians. We can find both. It's very simple to do that. So which one of these has theta by itself? This version, so that's the one we're going to use. So the length of the subtended arc, they say, is 2 pi. We're going to put that over the radius, which we say is 3. And that is the central angle measure already in radian version, right? Radian in terms of pi. It's 2 pi over 3 radians. Now, if we wanted to make this degrees, I hope you guys know you would just take this 180 and you would substitute it into this pi. So it'd be 2 times 180 divided by 3. 2 times 180 degrees divided by 3. And we find out that is a 120 degree angle. So either of those versions are correct for theta, but it's just, again, most of the time when you do the math, you're going to want this to be, this thing here primarily to be in radian form. Okay, so here's an example. Lizette and Alani are running a relay race. The circular track on which they are running has a diameter of 60 meters. Alani is positioned 89 degrees from her teammate. How far will Lizette have to run before passing the baton to Alani? So let's draw this one. It always helps to draw a picture. So here's our circle, okay? And the center of our circle is going to be right here, okay? And let's say that Lizette, it says, how far will Lizette, let's say Lizette is right here. Alani is positioned 89 degrees from her teammate. Now, 89 degrees, let's call this 89 degrees. So this is where Alani is. So there's on a circular track. So Lizette's going to start running. She's going to run this way right here. And at that point, she's going to pass the baton. It says, how far will she have to run? So that means this is what we're looking for right here. This is the subtended arc length. This is what we're looking for. Now it says the track has a diameter of 60 meters. Guys, diameters from here all the way across the circle. So if that's 60 meters, I hope you guys recognize that this would be a radius of 30 meters, 30 m. Okay, so all we got to do now is we got to figure out which one of these we are looking for, and we are looking for S. So we're going to use this formula. Okay, so that means we got to take theta and multiply it times the radius. Now, remember, she's not going to run in degrees. We want to know how far this is. So we need to take this 89 degrees and we want to convert it into radians. So this is going to be 89 degrees times pi over 180. Okay. And it's going to convert this into, again, this 89 degrees is going to end up being degrees on top, so we need a degrees on bottom to cancel it out. All right, so we got 89 times pi divided by 180. Okay, and that is going to be our theta. Our radius, we already know, is going to be 30 meters. That's right here. So if we do this, we should get the subtended arc length. All right, so we get our calculator out 89 times 3.14 divided by 180, and then times 30. So that means she's going to end up having to run 46 point, let's say 6. Okay. She's going to end up ending run 46.6, and the original measure was in meters. So that's how far she needs to run in order to pass off the baton to Alani. Okay. Right, and here's again an example of something we had before. It's just a way to do conversions between these three. It's not really conversions, it's using 2 to find the third one. Again, I'm going to focus on just this side over here really quick, so you can see what that is. So first off, again, it's about what you're looking for. Now remember, this is radius of circle A, so this is R. This is central angle, so this is theta. This is subtended arc, so this is S. All right, well, which one's missing here? S is missing. That means we use this formula. Okay, so it says to take theta and multiply it times the radius. Remember, theta has to be here in radian version. So we're going to take 270 degrees. We're going to multiply it times pi over 180. Okay, so that ends up being 270 pi over 180. And I hope you guys can see that you can knock those zeros off. And it looks like 9 goes into both of those. So we end up with 3 pi over 2. Okay, so we're going to take 3 pi over 2. We're going to multiply it times 8 because that is the radius. Remember, this is theta. Theta times radius equals subtended arc length. So 3 times pi times 8 times 2. Or 3 times pi times 8 divided by 2. So 3 times 8 is 24. So this is 24 pi over 2. So that is 12 pi. And so in our calculator, we get 12 times 3.14. And we end up with 37.68. 37.68 inches, because this is in inches. So this will be in inches automatically. So that's how long the arc is. If we go basically 3/4 of the way around a circle, all right, that's what 270 degrees is, okay, we will travel 37.68 inches. So this next one here, we've got, let's figure out what's missing. What do we have? What do we need? They give us theta, and it is in radians. So that's kind of nice. They give us the subtended arc length, 1.5, and what they're looking for is the radius. So what is missing? The radius. So we look for the one that has radius by itself. That would be this one right here. So this one is actually very simple. We're going to do the radius equals subtended arc length, 1.5 centimeters, divided by 1.05 radians, okay? And that's going to give us our radius, all right, guys? So 1.5 divided by 1.05, 1.5 divided by 1.05, and we get about 1.4, let's say 1.43. So this is about 1.43, and if this is in centimeters, so is this one, okay? And that's how that works. Again, this worked really excellently because the central angle is already in radians, okay? And how about when the central angle theta is missing, all right? So let's see how that one works. Let's use a different color. Go with purple. All right, so what's missing? You know, we've got the R, we've got the S. What do we not have? Theta. So that means we're going to be using this version right here, all right? So theta equals S over R. So theta equals S over R. The S is 8 inches. The R is 6 inches. So we're going to do 8 divided by 6. So in our calculator, 8 divided by 6 is 1.333 repeating. Now this is 1.33 radians. If we wanted to convert that into degrees, we surely could. 1.33 radians, we would just times it by 180, divide by 3.14. okay? And this would convert it into degrees. So in case you wanted to see that, 1.33 times 180 divided by 3.14. And so you're talking about, about 76 or so degrees, so, or 76 degrees if we wanted to do that. Okay, guys? So that's how you can convert between, not really convert, you can use two of these pieces of information to find the third. All right. And you should now be able to complete your check your understanding questions for section 13, topic 6, which again is called arc measure, but I kind of liken it more to arc length. On Algebra Nation, guys, this is your last assignment. When you finish this, regardless of when you finish it, you are done. It is technically due on the 22nd, but if you want to turn it in, you know, a few days late, that is perfectly fine. I don't have an exact cutoff date yet. I'll keep you updated. Look for that on Remind. But that should finish your concepts for Algebra 2. All right, guys. So when you complete that, stand up, do a dance, whatever you want to do, you should be pretty much done with Algebra 2. All right, guys. Really miss you. Wish I could see you. It is what it is. Have a great summer and all that other kind of fun stuff. And I'll see you guys later.